welcome to lecture series. Today we will discuss about row space of a matrix. So, what is that? And then we will also discuss about details about it also. Consider an M cross N matrix capital A, which is we call, I can write down like this, Aij over capital F. Let row 1, row 2, row M of capital A be defined as say alpha 1, alpha 2 and alpha n respectively. So, I am calling first row of A as alpha 1, second row of A is alpha 2 and mth row of A is alpha m respectively. So, certainly here alpha I, the ith row of A is nothing A I 1, A I 2 and A I n. So, alpha I is of this form plate. Okay. Since we have defined the matrix capital A over capital F, so each entry A I 1, A I 2, A I 3 all belongs to capital F please. So, this means that this belongs to also I can say F n, basically n tuple space please over the F please. Okay. So, I have defined my alpha 1 alpha 2 as the m rows of capital A please. So, this implies okay, let capital S denote in the set alpha 1, alpha 2 and alpha m. So, linear span of capital S, which is subspace of Fn, is a subspace of course, this linear span of capital S is also will be a vector space please. It satisfied all the axioms of the vector space. It is called as row space of matrix A. So, linear span of all the rows of capital A is basically give you row space of A, which is basically a subspace of the vector space Fn please. So, this implies, so dimension, if I want to know what is the dimension of row space of A is basically number of distinct elements of any basis of row space of A please. Okay. Now, to understand how to construct the basis of the row space of A, we need to understand something product of two matrices and the row space for the, if I consider two matrices B and say P such that B equal to P into A, then we want to see the relation between the row space of B and row space of A. This may not be clear. So, let me just introduce some elementary matrix theory concept here and then I will come back to the basically how to find the basis of a M cross N matrix space. Okay. So, consider P is K cross N matrix, a K cross M matrix over say capital F. and A is M cross N matrix over say capital F. Let B is equal to P into A. So, B is K cross N matrix, because P is K cross M and A is M cross N. So, P into A will be K cross N matrix over capital F, please. I mean entries of capital B is from capital F, please. B will have K number of rows. Let beta 1, beta 2 and beta k be the first, second and kth row of B. So, what I have considered, let me again rewrite this one, B is equal to P into A, okay. Beta 1, B is equal to beta 1 to beta k, this is this row, okay. This P matrix is equal to, I have written say P matrix into, I have already notated that first row, second row and mth row of capital A as alpha 1, alpha 2 and alpha m type. Let linear span of beta 1, beta 2 and beta k equal to W. Since B is K cross N matrix implies each beta I will belongs to again F n, that is n tuple space, please. As alpha I belongs to n tuple space F n, here beta I also belongs to n tuple space. Now, we want to see, is there any correlation between the subspace W, which is basically linear span of beta 1, beta 2, beta k, and the subspace Ls of capital S, I mean to say subspace generated by row of the A matrix, please. We know both of them are subspaces of the vector space F n, please. So, here W is a subspace of F n and Ls of capital S is also subspace of F n, please. This is given to us. I mean from the definition I am getting this one, please. Now, we want to check whether any correlation between these two subspaces. So, to understand that correlation, I have to also understand the algebraic relation between these two matrices, I mean the relation between B, P, A, please. Okay. So, let me quickly check what is the beta 1. Beta 1 is equal to what? Beta 1 1, beta 1 2 and beta 1 n. This is an n dimensional array. I will have also similarly beta k equal to beta k 1, beta k 2 and beta k n. Now, this one equal to, this is my B matrix, please. So, I will have say P 1 1, P 1 2 and P 1 m, okay. And then I will also have P 2 1, P 2 2 and P 2 m, and similarly P k 1, P k 2 and P k m. So, this is my P matrix and your alpha 1 is like this thing. Alpha 1 is nothing, I have written A 1 1, A12, A1n, then A21, A22, A2n and AM1 to AMN. So, this implies if you simply write down the beta 1 when all the n components of beta 1. So, this is equal to, if I write down only simply beta 1, which is equal to beta 1 1, beta 1 2 and beta 1 n. So, beta 1 1 is what? The first row of the B and first column of A when they multiplied each other. So, this means that this is equal to, I can write down your sigma P 1 j and A j 1. So, this j equal to 1 to m. So, first entry will be like this. Second one will be what? Again sigma P 1 j, first row multiplied the second column. So, P 1 j and I will have A j 2, A j 2 j equal to 1 to m, and similarly the nth one will be sigma P 1 j and A j n, j equal to 1 to m. So, this will be the nth entry. Each entry is basically finite sum place. So, I can write down this quantity as in a compact form. If you see it, I can have also P 1 common, suppose P 1 common, P 1 is common from this side, this from this sum, from this sum, from this sum. So, if I write down P 1 1, simply P 1 if I take common, I am getting what? A 1 1, and here also P 1 1 means A 1 2, A 1 2, and here also similarly P A 1 n plus P 1 2, A 2 1, then A 2 2, then again A 2 n, means this is my alpha 2 and first one is alpha 1, that is first row of the A matrix, this second row of the A matrix, and similarly you know what, say P 1 m, when you consider P 1 m, then I am getting again A m 1, A m 2 up to A m n. So, this means what? This is equal to, I can write down sigma your P j alpha j, j equal to 1 to your m. So, in general I can say that beta I will be sigma P I j and alpha j, j equal to 1 to m. So, what does it mean? So, this means that each element beta 1, beta 2, beta k I can express as a linear combination of alpha 1, alpha 2, alpha m. So, this implies what? Beta I belongs to your Ls of capital S, the subspace generated by capital S. This implies the row space of B W will be subspace of Ls of capital S. So, subspace generated by the rows of B matrix, which is equal to P into A, is a subspace of the row space of capital A. Okay. So, this is a nice result, I am getting this one please. If P is m cross m invertible matrix over capital F. So, this implies what? My capital B equal to P into capital A, this implies that P inverse B equal to A. Okay. Now, friends, arguing same way, I can again show that the row space of A will be subspace of row space of B. So, this implies that row space of A will be subspace of row space of B, row space of B. So, we got an interesting result that if we have B equal to P into A, where P is an invertible matrix, then row space of B and row space of A are same. This implies if R is row reduced echelon form or even row reduced matrix also, if R is a row reduced echelon matrix of matrix capital A, where A is M cross N matrix over F, then row space of R equal to row space of A, because since R is equal to some P into A, because R has been obtained as a multiplying from the left a sequence of invertible elementary matrices. If you denote that is equal to capital P, then by previous argument I can say that the row space of capital R is exactly equal to row space of capital A. Okay. So, now we are in the position to find a basis for the row space of a given matrix A. Instead of talking any M cross N matrix over F, I will consider now any M cross N row reduced echelon matrix over F please, because I know that both of, if you consider A is a M cross matrix and the corresponding row reduced echelon matrix is R, then row space of A equal to row space of R. Let A be an M cross N matrix over F. Let R be the corresponding row reduced echelon matrix. Let R has small r number of non-zero row, 0 rows, then these non-zero rows will form a basis of the row space of, since row space of A is equal to row space of R. So, if B is a basis for R, then it is also basis for A. So, I will not talk about A, I will stick to only R please. Let row 1, row 2, row R are the first, second and rth non-zero rows of capital R. Let B equal to, I am considering row 1, row 2, row R. Claim B is a basis of row space of capital R. I mean to say any element of row space of R can be written as linear combination of row 1, row 2, row R please. Let the leading entry in row 1, row 2 and row R appear in column K1, K2 and Kr respectively. Then quickly let us recall the definition of row reduced echelon form. We know R I j equal to 0 if I is greater than R. This is, we know, the condition for the row reduced echelon matrix is like that R I j equal to 0 if I greater than R. So, I can parallelly take an example so that we can visualize this concept. So, I will also consider say my R matrix as here as an example, say 1 0 3 0 2. Then second one is, let me take 0 1 2, and here let me take 0 minus 1, then 0 0 0 1 and 0 0 0 0 0 0. So, if I consider this matrix, is it a row reduced echelon matrix? Does it satisfy all the axioms? Yes. See, leading entry here K1 equal to 1, K2 equal to again 2 and second column, K1 means column number in which leading entries appear. So, leading entry is first row in first column, so K1 equal to 1. Leading entry in second non-zero rows appear in the second column, so K2 equal to 2. Leading entry in third non-zero row appear in fourth column, so K3 is equal to 4. And the last rows is 0 rows, so no question of leading entries place here. See, here there are 3 non-zero rows, so for I greater than 3 will be 0, that is clear from here. Second one, your Ri Kj will be equal to delta Ij. Okay, here I mean 1 less than or equal to j less than or equal to r please, because K1, K2, Kr. 1 less than or equal to I less than or equal to R also, this is also correct. And third one, your K1 less than K2 less than like this Kr. So, this is my condition for a M cross N matrix R to be row reduced echelon form place, and I can see this is satisfied here also. Consider beta equal to B1, B2 and Bn. Be any element of the row space of capital R. Then my claim is that beta can be written as a linear combination of rho 1 rho 2 rho R, and certainly because they are the non-zero rows. So, any element of the row space of R is basically linear combination of rho 1 rho 2 rho R only. Now, my claim is that if I write down any linear combinations, say beta which is equal to B1, B2, Bn, if I write down this is equal to C1 rho 1 plus C2 rho 2 plus Ck rho k, then if I compare the Bkith entry, I mean kith entry of the, see here K1, K2, Kr, they all belongs to basically from the set 1, 2, 3 and n, they belong to this set. K1 will maybe 2 or 3, it is depending on the matrix splits. So, like this only, as we have seen previous examples, K1 equal to 1, K2 equal to 2, K3 is equal to 4. So, it is again in the domain of 1, 2, 3, 4 and 5. So, they are n equal to 5. Now, if I see Bk, say Bki, Bki means kith entry of my beta, that is equal to what? So, if I take the linear combination of this, then they are kith entry. So, this means that, okay, so this is basically nothing, I can write down sigma Ci your Rij, I equal to 1 to R. So, if I compare the kith component, this will be sigma Ci and Rij, that will be equal to, let me take the example parallelly, 10302, 10302, 01201, 0120 minus 1, and the other one is 00, okay, 0001 and 00000. So, this is my this one, beta is equal to B1, B2, B3, B4 and B5. My K1 is equal to 1. So, this is I can write down is equal to Bk1, Bk2 and B3, Bk3 and B5. So, beta equal like this thing. So, this is equal to what? C1 10302 plus C2 0120 minus 1 plus C3 into 0 0 0 1 and 0. So, it will be sigma Ri j will be equal to Ki, Ci I equal to 1 to R. So, this means what? So, this is equal to sigma, this is equal to Ci and delta I k I. Actually, I could write down here, it will be j, it will be greater not to confuse, b k j, I equal to 1 to r and c I and here r I k j. Yeah. So, it will be delta I j, I equal to 1 to r. So, this is equal to what? This will be simply C j. So, B k j is equal to C j. So, this implies we will have C 1 equal to B k 1, C 2 is equal to B k 2 and C r equal to B k r. So, any linear combination is the rho 1, rho 2, rho k, and if you take any element beta which is belong to that space, then I am getting that the B k 1 equal to basically C 1, B k 2 is equal to C 2 and B k r equal to C r please. So, this implies also rho 1, rho 2 and rho r is also linearly independent. How? How? Now, because if I consider linear combination of these ones, since sigma C I r I j I equal to 1 to basically r, I can put it like this C 1 into, yeah, like this, C I into r I j equal to 1 to n please, yeah. Okay, so, this is like this thing please. Okay. So, if I consider any linear combination of rho 1, rho 2, rho r, that is sigma C I rho I equal to 0, 0 means 0 0 0 0 element. This implies that already we have checked that C I equal to 0 please. Any element beta which is equal to b 1, b 2, b n, which is a linear combinations of rho 1, rho 2, rho k, we have seen that the constant C 1 equal to b k 1, constant C 2 is equal to b k 2, like that. So, this implies that any linear combination of this which is valid for all the elements. So, it also valid for 0 element also. So, this implies that C I equal to 0 for I equal to 1 to r. Okay. So, this is the result please. Now, exactly same thing I can also show it here please. You see the right hand side is equal to C 1 comma then 0 3 C 1 0 2 C 1 plus 0 C 2 2 C 2 0 minus C 2 plus 0 0 0 and C 3 0. So, this if you simplify it I am getting what C 1 comma C 2 comma 3 C 1 plus 2 C 2 comma C 3 and then last one is I am getting 2 C 1 minus C 2. Comparing the coefficient both side B k 1 equal to C 1, B k 2 equal to C 2 and B k 3 is equal to C 3 please. So, rho 1, rho 2, rho r form a basis for the row space of the matrix R or row space of the matrix A. Thank you.